In this video, we are going to talk about time series visualization. Specifically, we are going to see how we can reduce the noise or smooth out the noise in graphs, letting the trends appear more clearly. For instance, we have here the stock price for Twitter during the pandemic between 2020 and 2021. And we can see that there are random jumps up and down, but there is also an overall trend going up during that period. So we might be interested in smoothing out all the small random jumps, smoothing out the noise, and let the general trend appear. This is what we can see on the graph with the original observations in black and the smooth line in red. This allows us to get a better overview of what is happening in the data, especially when there is a lot of noise. So one way to achieve that is to compute moving averages, also called rolling averages or running averages. They are simply a method where we take the average over some time period of width W, we call it the window, and it's usually an odd number so that we have as many observations we average over before and after the current point. For instance, let's say that the window width is 3, then we take the midpoint of W at the current observation, let's say t equals 5, and we smooth the value at this point by taking the average between the observation 4, 5, and 6. So we took the average over 3 observations, and the middle is observation 5. The more you increase the width of the window, the more you have a stable time series. So the more smoothed out it appears. There are a lot of good points. First, it's very easy to use, and it can make meaningful movements in a time series appear more clearly. Now, you have to define a value for W. It's subjective and can have a huge impact on the overall graph. And the more you increase the window, the more you require data. So we can use moving averages to make a very simplistic prediction, but they are not very reliable. One of the problems is that we need to have the observation ahead to make the prediction, because we take the average of the 5 observation before, for instance, and the 5 observation ahead. If we don't have the observation ahead, we cannot make a prediction. So instead, what we can do is take the average over the W last period. In that case, we say that we have a right-aligned window because we are making the prediction, we are averaging for the observation that is the most on the right of the window. So in that case, our prediction is just the average of the last W minus 1 periods. So here is an example of the Twitter stock with 2 moving averages. One is using a centered window in red. So I took 5 days before and 5 days ahead to compute the moving average. And in blue, we have the right aligned window where I took the last 30 days to make a prediction for the current value. So we can see that first we are missing in red the first 15 days and the last 15 days because we need them to compute the average. And if we go further, we are missing observation to compute the average. For the right aligned window in blue, we are missing the first 30 observations because if we go further to the left, we are missing observations to compute the moving average. But we have the prediction up to the last value. However, because it's taking the average over the last 30 days in blue, if you look to the right, you see that we're well below the current stock price. And that's because the stock changed a lot in the last few days, and we are still kind of stuck in the past by computing the average over the last month. So another way to smooth out time series data is to use simple exponential smoothing. This is a bit more advanced than moving average because now we are assigning more weight to recent observations. And as we move further in the past, we decrease the weight of each observation in our average. So you have the formula here on the screen, and you can see that our prediction for yt at yt plus 1, is alpha the weight times the current value of yt plus alpha times 1 minus alpha times the previous value of yt, so t minus 1. And we continue like that up to the first observation. If, for instance, the weight is 0.5, so alpha is 0.5, at the beginning we have 0.5 times yt, and then we have 0.5 times 1 minus alpha, so this is also 0.5, so 0.25 times yt minus 1. You see that its weight is divided by 2. And as we continue like that down the chain, each weight will be divided by 2 in that case, up to the first observation. We can also limit the window and say we are only going 100 observation back, then the weight becomes too small and it doesn't really matter for the current value. Now this long formula going all the way back to y1 is equivalent to the one you have at the bottom, which says that the prediction for yt plus 1 is alpha times the current value, yt, plus 1 minus alpha times the predicted current value. And the predicted current value, yt, depends on yt minus 1. And that's why it's equivalent. So if you plugged back yt hat, if you replaced it by alpha times yt minus 1 plus 1 minus alpha times yt hat minus 2, and continue like that, you will get the formula at the top. Selecting the appropriate weight alpha, which is between 0 and 1, is very subjective and depends on what you're looking for, but it has a huge effect on the result. If you use large weight, you'll have more credence, more weight on the recent observation. That will, however, increase the variance. If you have small weights, now it's more smoothed out and you'll have more credence to the accumulated history, so it's more stable as a time series, but it's also less reactive. What's good about simple exponential smoothing is that it's very easy to use. You can isolate more meaningful movement in a time series, and changing alpha doesn't impact the data requirement. I don't need to have more observations ahead. I can change the alpha, it's always the same number of observations needed. So here is the example of the Twitter closing price for the period between 2020 and January 2021. And we can see the two smoothed version, one with a weight of 0.2, so 20% in red. It's more reactive, it's moving more with the data. And another smaller weight of 5%, so 0.05 in blue. And you can see that it's more stable, but it's also kind of lagging a bit behind. So smoothing can be used for predictions, have we seen it, but it's usually pretty inaccurate, specifically when you have trends, seasonality, and cycles that we'll see further today. However, there are some modifications to accommodate for some of these characteristics of time series, one of them being the hot winter's seasonality adjustment, but we're not going to cover it in this course. In general, remember that smoothing is good for visualization. We can detect trend and see some general pattern, but it's pretty bad for predictions. And for that, we are going to move to econometric models.